yesterday we did I/O, and so we're at the point where we can write programs that either make up their own data and print it out, or that will read data from a terminal, a console terminal, or a file and write it out to another file, or any kind of stream I/O connection. And that was pretty much the way programs were going, and the way you wrote programs through pretty much the 70s. Around in the late 70s, early 80s, hardware developed enough so that you could get nifty bitmap graphics terminals, CRT monitors, and the graphics cards to support them, and processors that were powerful enough to go through and keep up and draw things on these nice new bitmap screens. Okay, these really just started to percolate in the late 70s, early 80s. And initially, people just duplicated the old CRT metaphor, where you had a character array that you typed in a line, and the program would use the stream concept and read that line and then print out some characters to it. So people just duplicated the concept that they knew. And after a while, people decided to get clever, and they figured out, well, we could put two of these guys up there. But still, it was the same programming metaphor. Things started to change pretty quickly, though, and the notion of a Windows system, or the technology of a Windows system, which probably parts of it were in existence and demonstrations were in existence back as far as '68, probably, but the hardware just was not cheap enough and fast enough to make it practicable, and it just started to happen in the early 80s. And Xerox PARC did a beautiful thing called the Alto, and maybe something before that, where they really pioneered what is the modern desktop and modern idea of Windows systems. That idea was picked up by Apple, and so they came out with kind of the first Windows system-based product, the Macintosh, I think it was. Simultaneously with that, at MIT, people were working with bitmap graphics and terminals and what used to be called engineering workstations, or bitmap workstations. And the people on the floor above me were working on operating systems for that, and Windows systems for that, and eventually gave up whatever they were doing their thesis on and ended up writing X Windows, which propagated around and is now pretty much the standard Windows system for Unix-based systems. And of course, later on, Microsoft picked up on the idea and came up with Windows and Windows 95 and 98 and 2000. So pretty much this window-based metaphor has taken over the programming world, and fewer of the programs you will write these days, unless you're doing pure web programming or pure server-side programming or middleware. If you're writing programs that interact with users, they won't be of the type that read a line of text from the terminal and write some characters back, like our friend JavaC does, for example, or read from a file and write to a file. That's a better metaphor for JavaC, I guess. But you would like to have nifty graphics, what's called GUI, or graphic user interface-based programs. That's kind of the standard for human-computer interaction these days. And so today we will start talking about the technology involved in writing graphic user interface applications. There's a lot of it. We'll probably do the next 3 lectures on various aspects of it. Today we'll talk about the basics of Windows systems, what's going on, and how to put up a window and draw stuff on it. Tomorrow we'll talk about the problem of getting input from the system. It's much more complicated than, or it's different, let's say, than the stream metaphor. It's a different metaphor, and it actually will have to change your whole way of programming because there's much more input to respond to. You have to respond to mouse motion, mouse clicks, keyboard clicks. You have to respond to things that happen in the context of this Windows system. So you have to respond to a lot of things. And the way people have found that it's convenient to organize programs to do that is quite a bit different from the way we've been looking at them so far, at least looking at control flow so far. So we're going to take kind of a leap tomorrow. And then on Monday and maybe Tuesday, if we run over, we will talk about how to use all of these components that are an integral part of these graphics user interface systems. Toolkits have built up in all of these systems, whether you use X Windows or Windows or the Macintosh. You're not in the situation where you have to do every application from scratch and say you want to do just this application. You don't have to draw every bit on that piece of screen. There are components, often called widgets, that people have built up and put in libraries and kind of do their own drawing for you and have some more abstract behavior. So you're not basically living in a mouse click dot writing world, which we're going to be kind of in today. We'll talk about that Monday. Again, I'm going to try and just give you the basic concepts and not too many of the details. There are a lot of details in using any of these things, and all you can do is look through the manuals and then go to the online documentation. If you look at Volume 2, probably half or more of Volume 2 and maybe a third of Volume 1 of these books is pure detail on how to write graphic user interfaces. And it's probably just, it's by no means complete. It's probably just the tip of what is really involved. The other thing about graphics programming and graphic user interface programming is that it can be very time consuming, not because it's hard or particularly complex, but as I say, there's a lot of detail, and it takes quite a while, I found, to get the visuals right. It's easy, the basic routines to draw things, to lay things out, and to make things look a certain way are pretty straightforward, and you can learn them in an hour or so. But then getting the thing to look exactly the way you want it to look, okay, is very time consuming, and to make it look good is very time consuming and takes a certain amount of graphic design talent, which I certainly don't have, and just takes a long time. There are tools called layout editors which can help you with this. Some of the people here have downloaded some tools like JBuilder, which I think has a layout editor that lets you arrange kind of your components on a screen, and kind of it will let you arrange your user interface look and feel graphically, so you can do it interactively, and then it will dump out a whole mess of code. Microsoft Visual Studio has a tool like this that you can lay out dialog boxes and things, and we'll talk more about this on Monday, I guess. I'm getting way ahead of myself. So I want to start out with talking about just what's going on in a Windows system, so you know what your program has to do, what the operating system is doing, and what the Windows system is doing. So if you look at the screen, you've got a bunch of stuff going on. If I put up more than these, you have a bunch of rectangular areas of screen which have certain properties that you can like move them around and stuff. And these rectangular areas, which I'm going to call frames, okay, each one of them is attached to a program. So this one is a rectangle of screen, and it's functioning as the input and output for a particular program, which is essentially a Linux shell. Okay, what I'm talking to is a T-shell program here, or in this one's probably talking to a bash program.
How do you know which programs they're talking to?
You know which programs they're talking to essentially because you either started them up from some command, or you, if you're the one writing the program, you know you created a certain window or a certain frame associated with your program. For example, here's one associated with Emacs. One way you know as the user is that there's usually a title bar, okay, that tells you what program it's associated with. Now, if you have multiple Emacs running around, it doesn't tell you necessarily which Emacs it is. So now, the mapping between frames and programs is not one-to-one. A single program can be driving many frames. So there's complicated applications that'll pop frames up all over the place, each one of which is controlling the input. There's also a lot of programs with no frames associated with them that are just running services in the background for you. And then there's programs like this terminal which have a single frame. So there's another set of rectangles we need to think about. If you look at this frame, there's a bunch of things going on internally here. For example, we have this area where text is displayed. We have this rectangular area which is functioning as a scroll bar. We have this area which is functioning as a toolbar. We have these areas which are functioning as menus. Okay? Each one of those is another rectangular piece of screen that has to be managed. All right? And those areas, rectangular areas, I'll call components. And so each frame, you can see, has a whole pile of components inside of it. If I start up one of these, okay, now I have two. I click here, and I type a command. The command goes to there. If I click here, and I type exactly the same thing on exactly the same keyboard, the keys and commands end up there. Okay? And there's nothing magic in particular about this clicking action. I could have changed it so that just moving the mouse from this window to this window would redirect where I put the where the characters would be. There's also drawing effects that are going on. All right. If I cover up one window with another and then shrink it, okay, the contents of that window magically come back. And if I move it around, only the part that you know, I don't get shadows generated here. So there's a lot of stuff going on, and there's really three players in this game that you need to keep track of who's doing what. There's the operating system, which is basically running the hardware. Okay, the operating system is talking to the or listening to the keyboard and responding to very low-level events from the keyboard. Somebody pushed the L down. Somebody let the L back up. Somebody pushed the shift down. Somebody let the shift back up. It's also tracking every little thing that comes out of the mouse that that corresponds to a movement or a click. And in addition, it's running this piece of graphics hardware that maintains the screen. Some of this, by the way, may be background and you just know all this, but just to bring everybody to the same level. And just a digression on this graphics hardware. What this screen represents is a rectangular array of dots. Okay? These dots are called pixels, and the basic operation that you can do with them is set them to be a certain color. So basically what's going on under the hood here is all of the dots on the screen are being set to various colors, which are making the image. One thing to keep in mind when you're writing programs like this is that not all screens are the same size, in that they don't all have the same number of dots. Okay, this screen.
How many dots?
This screen probably has, I'm guessing, maybe either 1024 by 800 or 1200 by 1000. I'd guess probably, I would guess, because the monitor in my room has is about 1000 by 800, something like that. Typically, the aspect ratios are 4:3, but they go down as low as older machines will have like 480 by 7 something dots, and the machine I have at home will give me 1600 across and 1200 down. Okay, and so I can write in very, very tiny letters on my screen. This is important because when you write these applications, you're often writing them in terms of the size, the number of dots. Okay, when you draw something on the screen, as we'll see, you say, I want to draw it 100 dots wide and 100 dots high. All right, now you size that based on looking at your screen that's like 1000 by 800. Somebody displays that on their screen that's 400 by 700, and that square that you drew is going to take up a whole much more of a smaller screen than it is on a larger screen. Okay, this is one of the reasons another reason why graphics user interface programming is hard, because you're starting now to get into the issue of variation between platforms. Okay, you want to make something that looks good on all platforms, and even if you're restricting it to Linux platforms, it's got to look good on, somebody with a small screen, somebody with a high resolution screen, and it's just something to keep in mind. I don't have a good answer of what to do about it because it's hard. It takes artistry and design to say, which information that I could display on a big screen I want to throw away to make a nice looking and still useful display on a small screen. So, little digression there. All right, so the operating system deals with the low-level hardware. Then there's a program called the Windows system, which on Unix runs, and under X Windows runs as a separate process. In Windows, Microsoft Windows, I believe, is part of the operating system or tightly coupled to the kernel. But conceptually, it's a different unit. And what the Windows system's sole job is to do is to manage the screen display and these I/O devices in such a way that all of the programs, can operate in a model that they themselves, they kind of have their own virtual environment looking out. So when you're writing a program for a graphic user environment, you'd like to think of your program as the only one running, that you have access to the mouse, you have access to the keyboard, and you have access to some rectangle of screen real estate. What you don't want to have to worry about is where on the screen that real estate is. You don't necessarily have to worry about whether it's shrunk or not. You don't necessarily have to want to worry about what other programs are running. Okay, and the Windows system handles all of that for you. So from the user's point of view, you've got all these wonderful windows running around. And from the programmer point of view, or the program's point of view, each program looks like it has essentially its own virtual window, its own virtual graphics machine with mouse and keyboard attached. And the only thing the program can tell is, for example, when I'm typing at this window just, the program in this window just thinks I'm not typing. Okay, so everybody thinks they're connected to the keyboard, but the Windows system makes it so that only the right program sees what's being typed. And this is an amazing amount of mechanism. This is just very clever when you start to think of what's going on. The Windows system also does a lot of nice things for you. It handles all of this toolbar on top. It puts on these buttons. It wraps the outer border on things. It does the moving. It does the shrinking or the iconifying. Which one? This one. It does the automatic resizing, and it handles this. Now, because your program, you notice that more characters appeared when I grew it. Your program has to react to that. The Windows system is communicating with your program and telling you what's going to happen, but the Windows system is doing all of that neat stuff for you. And the Windows system basically operates, the Windows system is managing all of these little rectangles, okay? Not just these frames, but it's also managing these components, because when I click on this rectangle, on this menu item, is that going to do something bad? No. Something different happens than when I click on that menu item, which I'm not going to do. And so the Windows system is intimately involved with all of these little rectangles, which we're going to call now windows. Okay? So these major things out here are windows, and generally all of these little rectangles in there are windows. And for most Windows systems, the basic rectangular unit that is filtering keyboard events and mouse events is the notion of a window, as we'll see tomorrow. And part of programming these things is organizing these hierarchies of windows and then taking input from the mouse and associating it with the right window. Actually, the Windows system is doing that for you. You just have to act on it properly. Let's see. One more thing I wanted to mention here. Oh, yes. These windows are arranged in a hierarchy, mostly based on enclosure. Okay, so this main frame window has lots of sub-windows, which are these component windows. It's got a sub-window that it's drawing this text into. It's got a sub-window that it's using to generate the scroll bar. It's got sub-window to generate this toolbar. Each one of these things is probably a sub-window. So there's this deep hierarchy of windows based on enclosure. Now, one thing that's important to remember and sometimes confusing is we're going to be dealing with inheritance in Windows systems plus enclosure. And the hierarchy that you generate by inheriting from various window classes or widget classes is different from the hierarchy of enclosing. Okay? In Java, there's this particular, add this window as a child of this window. So you basically are doing inheritance, which is giving you one kind of hierarchy. Then you're doing these gluing together windows inside other windows, which is giving you a whole different hierarchy. And it's important to keep those hierarchies straight because a lot of things propagate up one hierarchy and some things propagate up the other hierarchy. So, all right, I think I've talked enough about general stuff. Any questions, by the way, before we do something else? Okay. Now that I've talked about this, let's actually see how to do one. Let's write some Java. And it's remarkably simple to get started with one of these things. When we want a frame, in order to do an application that works like this, we need to get one of these frame windows. And in Java, we need to have an object associated with it, since it's object-oriented. And the object that we have in Java is called JFrame. All right? You can read in the book The History of the J. There's other things called frames. They've changed their mind a couple times on how they wanted this Windows system to work, and JFrame is the latest and greatest. And when we're using JFrame, although you can instantiate just JFrames, usually you want to take the basic JFrame that they give you and add on additional functionality. So almost always, you take these basic components that they give you, these basic classes that they give you, and extend them and inherit from them. So I made something called MyFrame here. I'm making a new class that inherits from JFrame, extends JFrame, and I've made a constructor. And the constructor just does a couple simple things. All these routines, all these methods are inherited from JFrame. One of them just says set the title, which tells the Windows system what to put up here. Set the size, that tells the Windows system how big you want to make it. You want to make this window. If you don't do a set size, JFrame defaults to 0, 0. So everything will compile fine, everything will work fine. You will start up your application and you will not be able to see anything. And then you will wonder what went wrong. And since there's lots of things that can go wrong, it's good to just get in the habit of doing set size so you can eliminate one thing. This line is a piece of pure magic, which I won't discuss except to tell you what it does. That means that sets up an operation so that when somebody clicks this upper right-hand close window button, the application will shut down. So just treat that as just a magic thing that does that. All right, so this is all my new extended frame class does. And now I need a test application to run it. So I have my public static void main. I just make one of these things. Okay, I instantiate one of these things. And you have to do the method you call to get the ball rolling is called show. Okay, this is a pretty simple program. One other thing I need to point out, all of this magic for doing the user interface stuff lives in a number of Java packages. Okay, when we did the I/O yesterday, all that lives in java.io, so you have to import java.io. javax.swing is the package that has things like JFrame in it. Pretty much anything with a J blah in front of it lives in Swing. Java.awt contains some of the graphic stuff for actually drawing things, and java.awt.geom contains more drawing stuff. So you have to put a bunch of these in, and you just keep adding them until Java's happy.
Putting java.awt.star doesn't automatically get...
You would think so, but it does not seem to. So I should be able to compile this thing, and now we can run it. And we get a little 200 dot by 200 dot, 200 pixel by 200 pixel window. I believe that the internal area is 200 dots by 200 dots. You don't get charged for this thing that the Windows system puts on, or this little border that the Windows system puts on. But look at all the cool stuff we get for just those, like, 5 lines of program. We get a frame. We get something that my frame pops up. We can move the puppy around, and we can shrink it, and my frame appears down here. We can grow it and appears here. What else can we do? We can blow it up. Basically, we have a whole Windows app just from those instantiating JFrame, because JFrame is the main class that talks to the Windows system and and between JFrame and the window system, it's the class that makes all this happen. So this is just,
Blow it up.
hmm?
If you blow it up,
Yeah.
the resolution is still that of the 200 by
No, if you blow it up, or resizing it actually does change the size. So as you see, okay, it'll start at 200 by 200 when I do this.
Although
But
any text that you had in there would not be
nothing,
changed. The pixel size would not change.
the window system will not change the contents. Okay, the window system will just change the overall size of the rectangle it's willing to give you for your frame. Okay, and you can adjust.
The resolution is the same no matter what the size is.
Yes, exactly. Yes. That reminded me of something.
So I think, well, it seems odd to me that you have to code that line for exit on close when so many of the other methods are just built into the class. You know, moving around, resizing, and so forth.
Yes. Well, because sometimes you might not want to exit on close. Say you had a program that popped up 3 of these. Okay, I could easily do my frame 1, my frame 2, my frame 3, and pop up 3 of these, and maybe only one of them was going to be my main window. The other ones were kind of just help windows or something. And so I didn't want to. I don't want to kill my app when I close Windows 1 and 2, only Windows 3. That's, I think, the thinking behind that. One other thing about resizing that. Oh well, it will come to me. So let's see. We did talk about resizing. Oh yes, when you do scale and resize, the Windows system, the JFrame, will tell your program that it's gotten bigger and smaller, but it's up to you to decide what to do with that information. Okay? By default, as we'll see in a sec, the Windows system will just clip. Okay? It will just cut off your application. So let's first try out that click on kill, and indeed my program went away. And it returned nicely, and if I do a PS to make sure I don't have any Javas running. So always good to check every once in a while. If you're not careful, you can get zombie Javas running around. So now let's try and draw something. All right. In general, you don't want to draw into your JFrame. JFrame is just this thing that interacts with the window system and gives you a place to pack other windows into. So what we're now going to do is start building this hierarchy of window enclosures, and we need a window type, component type, that is good for drawing on. And the one that's good for drawing on in Java is called JPanel. And I think I have a JPanel in this other thing, which I could just copy. Much as I'm sure you enjoy watching me type. All right, and so again, we want to inherit from JPanel because we're going to want to add behavior to JPanel. And so I have a class called MyPanel, imaginatively. And what I'm going to override, okay, what I'm doing here is putting in a method called paintComponent. All right. And paintComponent is not just a random method that I decided to add to JPanel. It is a method that is inherited from JPanel that I'm overriding. I'm not making this up from scratch. It's a method that this inherits. And it's a very special method, as we'll see in a second. So the moral of the incantation, okay, message here is if you want to draw something, you add your draw commands to the paintComponent method. All right? And the first thing you do in your paintComponent method, and this is another incantation, is always call super.paintComponent, which calls the paintComponent of the JPanel method, the kind of default paintComponent. And all that does is sets up the background and just makes your drawing look better and go nicer. Okay? So if you do this, things will look better. And finally, we get around to a drawing routine, and some of the drawing routines are pretty simple looking. Okay, here's one called drawstring, and we call it. Drawing routines are on this thing called graphics. Okay, there's a fair amount of magic going on here, some of which will not make sense until tomorrow, so you'll have to take my word for it. But when you put your routines in this paint component method, this paint component method, which you're overriding from JPanel, always gets called with this graphics object. Right? Now you're probably wondering, who calls paint component, and where does this graphic object come from? Don't ask that question. Just believe. We'll talk more about that tomorrow, but just believe that it happens. A certain amount of programming is just, believing ridiculous assumptions and then going on from there. But graphics, this graphics object is basically where all of the, well, you would think of as drawing routines live. Okay, it has a whole collection of routines like drawstring, drawline, draw rectangle, draw point, draw image, all these sorts of things. Anything that you can think of in two-dimensional graphics, kind of non-spiffy graphics, is living on graphics. All right, and drawstring is a pretty simple one. It takes a string, which is the thing you want to draw, and it takes coordinates, which are where you want to draw it. Okay. Now, a couple things about these coordinates. They are in terms of pixels. So we're drawing something 50 pixels over. We're going to start the string 50 pixels over from x and 50 pixels from y. Now, given we're using these coordinates, we need an origin and a coordinate system for these to make sense. And somewhat counterintuitively, the origin for drawing in a panel is the upper left-hand corner of the panel. 0, 0 of this panel would be this part up here. Okay? It's the upper left-hand corner of the particular window that you are drawing in. So it's not the upper left-hand corner of the frame. Every little window component, whether it's a component or a panel or a frame or a button, has its own coordinate system. So when you draw in it, you can draw in it locally, in its local coordinate system, and you don't have to worry about either where it has been packed in the frame or where the frame is on the screen. Somebody else worries about that for you. So that's great. The other thing that's a little counterintuitive is that y increases downward. This program should draw, this panel should draw a hello world up in the corner here. But we're not quite done. We've made a class myPanel, but we've never done anything with it. And in these things, the main program is still where we start executing. So we've got to go make some stuff.
You don't have to make a new graphics object then.
No, the graphics object is supplied to you as if by magic by the technology behind all this.
Is it a Windows system that's calling the graphics object, calling the paint component?
It's somewhere between the Windows system and the implementation of JFrame or the component set. Okay. Sometimes those are combined. In Java, they're really glued together. So the Windows system and the component set are closely coupled. In X Windows, okay, they are much more separate. So the Windows system is actually a process that communicates via this network protocol, actually, between all these component sets. So in that sense, the graphics things would be a little bit more decoupled from the actual thing that maintains the Windows. The magic of that and the beauty of X is that, given they do it that way, using this protocol, loosely coupling things, you can actually run a graphics program, the program on one machine, as you've undoubtedly done, but have the display on a different computer. Okay, that's something that comes very naturally to Unix users and X Windows users. If you go to any other environment, you miss that very quickly. So here we're creating a My panel, just the way we did a My frame with instantiation. Some magic here. Okay, container frame, blah, blah, blah. And this add is the basic operation for taking one window and putting it inside as a child, not an inherited child, but in this enclosure hierarchy of another window. So what this add is doing is it's putting the panel, which we just created, as a child inside the frame window, which we created before. The book will explain what this is. So this is kind of a magic window in between this one and this one. It's not worth worrying about it. It's better just to always put that stuff there. Let's see. Let's get rid of that. Let's try and compile. And there we have Hello World. Pretty cool.
The panel doesn't have to be the whole size of or the whole size of the frame.
Right.
But we didn't do anything to specify.
I didn't set a particular size on the panel. All of these windows you can individually size. Since I didn't size it, it just defaults to as much area as it has. So here's our Hello World. And when we move our window, the Hello World moves along with our window, which is nice. It's 50 dots over and 50 dots. It starts 50 dots over and 50 dots down from our coordinate, which is just where we like. Now, one thing that you may have noticed is that we put that drawstring in our paint component method that we inherited from our friend JPanel. You might ask, why didn't we put those draw routines in main? Okay, why? Because normally we're used to putting our program stuff in main, the stuff we want to do in main or things that are called for main. This paint component method is weird in that we never called it. Okay, you would think that we created a JPanel in main, but we never called this method. So why couldn't we do the drawing in main? And in fact, if we really tried hard, we could. One reason we couldn't is we'd need to get a graphics object. But since we have a JPanel, we could ask the JPanel for its default graphics object and then call drawstring from main on that. But here's a cool thing. Notice when I cover that up and then release it, it's still there. Okay? If we had called drawstring from main, all right, what probably would have happened is it would have come up fine and looked the same, and it would have even moved around. But when we covered it up and uncovered it, it wouldn't be there anymore because we had only drawn it from main once. Okay? Actually, there's two ways you could imagine this mechanism happening. One is that the Windows system keeps in memory someplace a bitmap consisting of all the current contents of each window, and then basically just when you uncover this window, it just refreshes what the area that's visible with the bitmap it keeps in memory. Okay, and so it could have done that to all of these windows, and all that would work. But that's actually not what's happening. Okay, every time, because that would take up quite a bit of memory. If you had lots of big windows with lots of stuff going on in them, the Windows system would have to keep all that around. What's actually happening is every time something interesting happens here, like something being uncovering, it's not that interesting, the paint component method is magically being called again. And that's why we put that stuff in paint component. We can even see that. Let's do something in our paint component method.
New typo.
All right, I'll catch it in a sec. Yikes. It's very strange to type when stuff shows up over there. I'm not a touch typer, so I need that feedback. All right. That should be one of those. All right. I think we got that. Terminal. All right. So when the thing popped up, we can see our paint component method got called twice. Now, if we move this guy around, nothing happens. We move it over here. We're covering it up our window. Nothing happens. Okay, now we start to uncover pieces of that window. And suddenly, the window system says, oh my God, this guy's getting uncovered. We got to refresh it. So it starts calling my paint window routine like mad. Okay.
Would it have called it as you moved that window around?
Well, let's see.
Does Swing must buffer and do nice graphics things to not?
Swing buffers to the extent that it will avoid the flickering. Okay. One of the effects you will get if you have on some older Windows systems, let's say, is that if you have a nice picture up there and you're refreshing it, a lot of times your first instinct is to, okay, I'm going to clear the background and then I'm going to draw everything over again. All right? Because every time this paint routine calls, it's got to redo the entire picture. If you do that, you will notice that the thing is going to flicker like mad, because when you do that clear, you're going to get a white background for a second, then you're going to draw everything, and that's often just at the edge of perception, so you get this very flickery effect, which is distracting. So what lots of Windows systems do is they will create a temporary array, maybe take all of your graphics commands, draw into that, and then once you've completed your new picture, swap it for the old picture all at once, which gets rid of that annoying flickering. So the question is, what happens if I move this around? And no, because, oops, why did I do that?
It's because you went under the.
Oh.
Yeah.
So as long as as long as the Windows system can maintain the state of this thing just by copying the current bit around. Oh, if I resize it, it's going to go nuts. So the Windows system kind of has an idea of when this piece of screen area has changed or needs to be updated. And if it's just moving it around, okay, then it can just copy the whole rectangular array of bits or pixels around and doesn't have to go back to the program to say, what do I do? But if you start to interact with other programs, or let's see what happens. Clearly, if we shrink it and grow it, it's going to call us again. Poof. One thing also you will notice from that is that as the thing is gradually being uncovered, this paint component is being called a lot. All right? So if this paint component is very slow or is taking a long time, your update is going to start to be slow. Okay? You're going to start to see, as you drag it, some blank spaces behind the window as you're uncovering it, and then gradually they'll kind of fill in as the machine catches up. But something to think about when you're writing your paint components, if you're really sophisticated in doing this and want to do it for real, this graphics object will tell you when something's been uncovered. It will tell you just the sub-rectangle of your window that it thinks has been damaged and needs to be changed. So if your drawing routines are very clever, they can realize that if only the bottom right-hand corner has been damaged, it won't try and do all the stuff that's in the upper left-hand corner. It'll just keep that and only update and only redraw the parts that have to be redrawn. Unfortunately, your system has to maintain that on its own. And if you think about it, that means that you've got to have some fairly sophisticated data structure that knows where everything you've drawn has appeared in what part of the screen. So, well, that's the essence of drawing things. So all we can do now is like draw more stuff.
If we wanted to change the font size of Hello World, would that be in the My Panel, in the paint component method?
The thing that remembers, okay, that's a good question. The thing that remembers all sorts of properties about how to draw things is the graphics object. Okay, so this is kind of going to remember current font, current color, current line width. So whether you're drawing thick lines or thin lines, the line style, whether you're drawing dotted lines or dashed lines or complete lines. It probably remembers some properties about how to draw corners, so you can get rounded corners versus squared corners on rectangles. If you look in the documentation on the graphics object, there's just lots of routines to set stuff. Okay, so well, let's try. Yeah.
Can you explain again how drawstring is being called?
Okay, well, drawstring is being called from paint component, right? That's clear. I have this nice method. How is paint component being called? That I really can't explain until tomorrow. Okay, but paint component is essentially being called from the Windows system or from the piece of magic behind all this that's making it work. One of the things we can draw is rectangles. So I might have some stuff in here to draw rectangles. I don't, but I do in your notes. So let's, not that guy, this guy. Yes? All right, here is a, let's see, a little snippet to draw lines and rectangles. All right, good point. Let's grab all this stuff and go back to Emacs. I hope this works. Yes. Get rid of text. All right, and we'll just go through this.
Now we're making a new graphics 2D object
Right.
within the original graphic object. Is that?
We'll just step, there's a lot of different things we're doing, so let's step through them, okay? First thing we're doing is we want some colors, because we're tired of black on gray. So we want to get some colors. And so colors in Java are mediated by a color object called, appropriately, color. It's a class called color. And colors in computer graphics are ultimately represented as triples of numbers. One way to represent the color space is the amount of red, the amount of green, and the amount of blue. Okay, if you study paint and additive color formation, you can make any color from adding certain amount of red, certain amount of green, certain amount of blue. It works not quite the way it does with Play-Doh, since Play-Doh is subtractive color. So if you take red Play-Doh and blue Play-Doh and mix them, what do you get? Purple Play-Doh, right. If you take red Play-Doh, or if you take red light, which was what we're generating here, and blue light, and mix them, what do you get? You get magenta, okay, which is...
But RGB, they're not the primary colors, are
Red, green, and blue.
They're
not. Green is blue and yellow.
Oh, right, but no, they're the primary colors for addition. The primary colors for subtraction are, what is it? Red, blue, yellow, yes. Red, blue, yellow, yes. So in fact, if you want yellow, you take green and red. Green and red make yellow?
I think so.
Okay. So,
In Plato.
no, in light. Okay, so we can actually do this. Right now I have red, but let's make a new color. All right. So let's see, here's red, here's green. Let's do some red and green and see what we get. Another thing about these color amounts is they range from 0 to 255 in general. So you basically get, you can select the amount of red you get from 0 to 255. All zeros will give you black. 255, 255, 255 will give you white. 255 in any one of those will give you bright red, bright blue, bright green. Intermediate mixes, you have to fool around with a little. Because one of the things about color displays is that they are not linear in color. Okay? If you double the color number, it does not double the perceptive brightness. Okay? There's a whole science of this called gamma correction, which people who are really interested in graphics and photorealism on screens, and Philip can go on forever and ever and ever about gamma correction. So if you want to learn about it, ask him. So we made some colors. There's some built-in colors that are arranged as static variables on the color object, so we can have the color blue just by accessing this color.blue. And that will, there's some static ones that are already made up for you. And there's a handful of colors in Java. There's maybe a dozen or two colors that are done for you. In XWindows, if you're using the raw XWindows interface, there's probably 100 colors, like dark brick red and burnt sienna, and your whole Crayola box of colors are done out for you in XWindows. And you can get those from the screen. This graphics 2D thing, all right. As you'll read from the book, Java seems to have changed its mind, or Sun seems to have changed its mind or design again between the 1.2 version of Java and 1.3 version of Java in how it would be neat to do the graphics objects. Okay, and you can draw your own conclusions about which way was better. The old way would have a routine called draw line or draw a rectangle, and you'd give it the coordinates of the rectangle. For a line, you give it, the right-hand x, y coordinates and the left-hand x, y coordinates. And for a rectangle, you give it one corner and a width and a height. The new system is even more object-oriented and involves classes for each type of thing. So if you want to draw a line, you have to make a new line 2D. And if you want to draw a rectangle, you have to make a new rectangle 2D. And then you call operations on them. This isn't going to work because I don't have anything to call on it. So you take the graphics object called draw on this object, and all of these new routines are packed on this thing called graphics 2D, which is a subclass of graphics. So that's why I'm downcasting to get this G2. Okay. One other feature of the new system is that pixels are now stored in either floating point numbers or doubles. And apparently there was some debate as to which, because they give you classes for both, designed with this strange syntax. What's really going on is there's an inner class called float inside line 2D and an inner class called double inside line 2D. So you have to select which one you want. Since I'm passing in integer coordinates, it's not going to give me too much trouble.
Float numbers always had to have F at the end of them.
float numbers do, but I'm hoping this is going to convert my integer to a float. If I did 100.0, I think it would give me a hard time. But if I just do, it won't convert double to float without complaining, but I think it'll convert into float without complaining.
Well, if pixels are discrete objects, why do you need more than integer?
A very good question, and one you should address to the Sun people directly. One concept I can think of is as follows. Say we did want to deal with this problem of scaling. Okay, you say you wanted to make something that worked on a 1,000 width screen and a 500 width screen, and you wanted to do it without, one way to do it would be to just essentially have some canonical size and then divide all of your pixel numbers through by the correct ratio. All right?
You could do integer. You could do integer.
You would think.
division.
Right. Another concept is if you wanted to do your either PostScript or DVI does, represent your screen in kind of screen-independent terms like inches or centimeters or whatever, and fractions of those, and then at display time, kind of recompute what coordinate system or what scale you wanted to display on a screen or a printer or whatever. I admit all of these explanations are, you could say, weak. Okay.
How many 2D objects have inner classes called like float or whatever? If float is already a reserved keyword.
Let's see. I think in part because I spelled them wrong. And that may be all of it. All right. Well, now we'll get the real answer to that question when we try and compile this thing. Kill. Ah, look at that. So what this is hopefully going to do is, okay, we've created a new line here, okay, with our magic create line command. Our set color red, so it comes out red. And we're setting, remember, we do all of the property sets we do on the graphics object, not on the line object. I don't know why. It would seem to be logical to do it on the line object since it's a property of the line, but then we do this draw, which just draws it. Here we create a rectangle, we set the color blue, and here we're doing fill instead of draw, which gives you a solid thing. And there's an equivalent thing rather than rectangle, there's ellipse object, which you could get ellipses and circles out of. And again, all these things have the same property that you can cover and uncover. And so it occurs to me that we did not figure out what red plus green was. So I want to go and do that now because I'm curious. Yes, yellow. Excellent. Okay, one more thing you can do with this package. Actually, there's a lot of things you can do with this packages. And you can see very few lines of code will get you a pretty lame picture, but nonetheless, with all of the properties of a fancy application. It's seductive in that you can easily build things up, and then you start to try and make it look really good, and that's where really the time ends up. So one last thing you can do is images. Let's see if I have some code in the here's some code which may or may not work. Let's go back over here and plop it in there. All right. There is a I'm just going to get rid of some comments because I just hate overflow lines. In order to get an image, there's some nice utilities that will do a lot of the work for getting images for you. And they are on this thing called a toolkit. Okay, there's actually a lot of neat things on Toolkit. Toolkit is where they've hung a whole mess of random system-dependent stuff. For example, if you need to get the size and resolution of the screen, you can access that from Toolkit. If you need to get, I think there's methods for creating, aside from images, fonts, I think, are all done off of Toolkit.
Are the functions in Toolkit guaranteed to be on every implementation of a Java platform, or it's then I mean, the get image that loads a JPEG may not be?
Yeah, I'm not going to promise that they are. I think that JPEG and GIF may be everywhere, but the toolkits are, as he pointed out, system dependent. So to get your own system dependent toolkit, you can't just allocate one. You have to go call a static method on this toolkit thing called getDefaultToolkit, which will give you a toolkit. Okay, kind of a weird way of doing things, but that's the way you get the particular system-dependent one here. And then once you've got it, you can do pretty straightforward things. Get image from a file name, and then draw image. We're going to draw it at, let's see, this will cover up all of our beautiful stuff. So let's draw it at 150.
You said use static method on S to get the system toolkit. Did you need to use S as an argument to it?
Oh, I just deleted a bunch of comment stuff. Your notes have the real comment. I just didn't like it overflowing the right. The size of the image is basically done on the image file now. I think there are utilities in here for scaling, but I haven't tried them. But so it's going to basically read this image off of the disk and just display it in its natural size. And if it doesn't fit, it's just going to clip it. All right? Right. So let's try this again.
Get image doesn't throw exceptions that we need to catch for file operations and things like that?
Apparently not. Apparently not. You would think it would, wouldn't you? But I think, how could it not?
From file, it must be eating them.
Or it might just, since it has a return value, since it's not a constructor, it might just return you null, okay, if it can't find it. It might return you a null image if it can't find it, as opposed to file input stream. Since it's a constructor, it can't return null. It's got to do something, so it has to throw an exception. It's got no choice. One of the things about draw image, no, it's there. One of the odd properties about draw image that the book will talk about is that it is what you could think of as a non-blocking call or a non-blocking routine, in that it returns before all of its work is done. Okay, so draw image will return, at least the first call to draw image will return before the image is necessarily loaded. The reason they did that was you can also load from a URL, and the URL might take a while to download. So that mechanism lets the rest of your drawing get going, and draw image just sets up something that says get this image and put it in the right place. So I'll bet you if I grow this, and I grow this to more. All right. So some of this update on the images I found is a little weird. And I'm not quite sure why. It seems to be, oh, I guess it's just slow. I guess I'm just impatient. So that's the only image I found on my desktop when I burned the CD last night. So that's what you get.
Now, we drew the line first, and then we drew the square, and so the square is on top of the line.
On top of the line, right? And we drew.
Is there a way to set priorities as to who should always be on top or something, or is it just by order?
It's purely by order, because remember, what you're doing is essentially setting bits in this bit array. So once you turn a bit red, it stays red until you turn it some other color. It kind of takes a while to load that thing and display it. So the draw image routine kind of sets some magic going in the background that says, load this guy and draw it here, and then returns. It doesn't wait until all the work is done until it returns. That's so you can start a whole mess of images going in your code, and they all go kind of in parallel. It's kind of a fancy optimization that they put in. Some of that time it was just loading it. Some of it might have been waiting for me to open the display and wait for paint image to be called again. Okay, it might have needed paint image to be called again for the display to actually have happened. So I could have put 2 calls in there right over each other to account for that. Draw image is a little strange. The book goes into a lot more detail about this effect of draw image, and their discussion is better than mine. So I will recommend you to the book. I just wanted to give you a flavor of what you could do with the graphics objects and images. So that's about it. Now you have the capabilities to do all sorts of cool things. No. Yes. Well, it's true, and you know.
Maybe it was just me, but we found circles aren't round really well.
Oh, the circles aren't round really well because your intuition for drawing a circle is to draw a circle that is X number of pixels across and X number of pixels down, right?
No, it's to draw an ellipse that has
Right, an ellipse with the same X and Y coordinates, and that assumes that pixels are square. And in general, pixels are not square. So you have to figure out what the aspect ratio of the pixel is in order to get your circles truly, truly round.
What are pixels in size?
I'm afraid that's probably monitor dependent. So I won't even say.
But they're sufficiently small that what difference would it make?
Right.
But they're sufficiently small, what difference would it make if they're square or?
Oh, well, what I mean to say, okay, a better way to tell you to say they're not square is that the pitch in the horizontal direction and the pitch in the vertical direction is not necessarily equal. So although the pixels are essentially overlapping points of light, their spacing is not guaranteed to be isotropic. So, okay.